So I want to do a series on historical metrology, a series of videos, and I'm going to start with this book, Historical Metrology by Berriman. So it's from the 50s. Berriman is an English engineer and he was a professor at Oxford, and he was very interested in this subject of historical metrology. So here is the opening page, if you can see that. There we go, and a little illustration on the side. I love these old books with the illustrations. And it was written basically as a side project. So this wasn't his paid work. Historical metrology was already out of fashion. But he really spent a lot of time on this, and it's a really good place to start if you want to find out a little bit more about historical metrology. Now, it might sound a bit dry, units of measure from the ancient world, but it's so interesting. So I'm just going to read a little bit from the book, and I'm just turning the pages. So in the start, there is a little section, Socrates on measure and weight, according to Plato in the 10th book of the Republic. So here it is. Immersion in water makes the straight seem bent, but reason thus confused by false appearances is beautifully restored by measuring, numbering, and weighing. These drive vague notions of greater or less, or more or heavier, right out of the minds of the surveyor, the computer, and the clerk of the scales. Surely it is the better part of thought that relies on measurement and calculation. So a nice little opening here from the Republic, from Plato, all about the importance of measure and calculation. And for Socrates, it was very important to try and get past illusions and to try to get back to the source, get back to truth and the light. And so he's saying, there's this optical illusion of you put something straight into water, it can seem bent under the waterline. And he's saying this is a fool's appearance. But if you measure and if you compute and if you calculate, then you'll arrive at something that's more truthful, that's more true to maybe what reality is. Okay, so then there's a list of contents in the book, all about Egyptian, Chinese, Palestinian money, a list of illustrations, and then we get to the preface. Here we go. Here's the preface. I have to say, this book was recommended to me by a friend, David Kenworthy, who's also really into historical metrology. So thank you for that reference. It's such a great book because it's his personal work, Berriman's personal work, but it's also such a great sort of compendium. And if you leaf through, he's got so many little tables, like this, and you can just have a quick check if you want to look up a particular unit. A few illustrations as well, like here. And anyway, let's go to the preface. Okay. On the 11th of May, 1951, the Departmental Committee on Weights and Measures Legislation published a report recommending the ultimate abolition of our present standards in favor of the complete adoption of the metric system, including the decimalization of the coinage. So this is something that many people are still not recovered from, the change of systems of measure that happened in the 50s in Britain. So Berriman is English, so he's talking about the UK, the change over to the metric system. And the coins as well. So the money system changed as well, and it was decimalized. And I think a lot of people still feel quite a lot of nostalgia. In fact, one of the things that happened with Brexit, so 10 years ago now, was this return to the imperial system of measures that was used then on especially on packaging. To continue, this is a matter that touches everyone: industry, commerce, the home. All would be affected by such a change, and a heritage of great antiquity would disappear from our daily life. Great antiquity. It is not my purpose here to discuss this recommendation, but to say something that has not been said before about our weights and measures themselves. It is their history, and their relationship to others that were used elsewhere in the remote past that come within the scope of historical metrology. So this book was actually published in 1953, first published, and the change of the law for the weights and measures was 1951. So this must have happened kind of coming up to the end of a long period of study for him. So what he's talking about here is this sense of great antiquity, this heritage of great antiquity. So he's actually talking about this link that he still felt that we had to the ancient world through the system of measures. And he's talking about how all these units are connected not only to each other, but to us. So it's a good place to start the book. Then he continues, this book begins with an introductory summary of the results of research on which I spent much of my spare time for 10 years, and I acknowledge with gratitude unrivaled facilities extended to me in the libraries of Oxford University. It was only by chance that I read anything about ancient measures, and my interest in their origins remained casual, until I happened to notice that published lengths of the royal cubit could be expressed plausibly by 20.6265 inches. So that's the first number in the book, and there are quite a few numbers. So you do have to kind of get over your fear of numbers if you have one. It's not that difficult. You don't need to be good at maths, but you just need to be able to look at numbers without shuddering. So he's talking about this royal cubit. He's talking about the Egyptian royal cubit in particular. And it's quite a famous unit. There are cubits, rods, if you like, sticks, units of measure, like rulers that have survived. And they're really mysterious. They don't work like our rulers now with nice, evenly spaced out markings. And it's interesting to see what length they are. And they're all in the kind of the same region, but they're not necessarily identical in length. Then you can derive the length of the Egyptian royal cubit from old temples and pyramids. But again, there's not always agreement. So it's in the region of 20.62 inches. It could be 20.618, 20.625, and he's saying 20.6265. And he likes this number. And importantly, it's expressed in inches. Let's continue. As this number has geometric significance in terms of the inch, it seemed to offer a clue worth investigation. And this further inquiry I was willing to make because for numbers I have the liking that should be inherent in an engineer, and he is an engineer, and also because metrology lies at the root of all the sciences that are concerned with the interpretation of measurements. If a study of archaeological records could reveal an intelligible history, it seemed almost a duty to make the search. So this is interesting, a duty to make the search. He stumbled upon something and he feels he needs to bring this knowledge back to the fore. He stumbled upon something that he thinks is really significant. And it tells us something about the ancient world, but also about ourselves and our heritage. And he uses this word heritage. And that's the first mention of the word archaeological. So he's an engineer, he's a scientist basically, and he's looking into the past because something has captured his imagination. He's realized something and he's pursuing it. Following the introduction is a section explanatory of my analytical apparatus and conventions and terminology. And then comes the evidence in detail arranged geographically, with the Far East represented by India, China, and Russia, placed arbitrarily before Babylonia, Egypt, and Palestine. An analysis of the earliest monetary evidence precedes a section combining Greek and Roman metrology. But any further reference to the metrology of numismatics would be outside the scope of this book. French pre-metric metrology is followed by a brief chronological notes on the history of the metric system, and the remainder of the main text is devoted to the historical aspects of the weights and measures of England and of those used in the United States of America. No chronological significance is implied by this arrangement, and even the geographical boundaries are blurred by overlapping provenances. Some notes that are not strictly relevant to the main theme will be found in appendices, but there is no place in which properly I could refer to the earliest mathematical texts. It must suffice, therefore, to remark that they should be studied in parallel with ancient metrology, not only as an aid to perspective, but also to sharpen opinion on the right answer to a particular question. Was the Earth measured in remote antiquity? Oxford, 1952, AEB. Was the Earth measured in remote antiquity? Well, anyone who studied ancient metrology will feel that they are fairly sure that they have an answer. So moving on to the introduction now, introductory summary. This inquiry reveals the oldest extant weights and measures linked by significant magnitude ratios to those current in historical times, and suggests that this ancient metrology was geodetic in origin. Okay, so two things going on here that are interesting. In the first sentence, he's saying that the very, very oldest weights and measures, they're all connected to a system with ratios that are significant and connected to our current historical times, meaning our time in history, which is evident through the measurements, the sense of this long, long continuity that can be quite surprising if you don't know about this already. And so this idea of ancient metrology being geodetic. So geodesy, which gives us the word geodetic, is, well, the etymology of the word means the division of the earth. And this could be in relation to a field. So the science that goes along with the practice of surveying. So you kind of dividing up, say, a field of land or even a country into measurable portions, often with triangulation. And through this surveying process, you're coming up with this kind of abstract figure, if you like, that can then be projected onto paper to become a map or online. So geodesy is this sense of dividing up the land to produce measurements, to produce a map. Maybe this could have political, cultural significance like boundaries, borders, property. And then this could also apply then to the planet Earth as a sphere. So geo means Earth, so it could be in reference to a piece of land or a country or a continent or to the planet. So when Berriman says geodetic here, he means the planet as a sphere, as a whole. One aspect of this hypothesis associates a linear scale with the sexagesimal division of the Earth's circumference. So a linear scale, that means units of measure that are linear. So as opposed to 3D. So if I pick up this cup here, well, anything in the real world is actually 3D, but in theory, you could talk about something that is just a line, so linear. And this is what he's talking about, so linear measures. And he's saying that they're linked to a sexagesimal division of the Earth's circumference. What does that mean, sexagesimal? It means the system of counting in sixes. So this is the system that we have to this day. So 360 degrees, and then minutes and seconds. So 60 and 60. So 360 is already 60 and 60 times 60. No, 6 times 60 times 60 times 60. So it's sexagesimal. What he's saying is that these linear units are linked to this division, this grid system of our planet into the sexagesimal system. So degrees, minutes, and seconds of arc. Then he says another implies that a decimal fraction of the square on the Earth's radius was adopted as the area for a land unit. Also very interesting. So now he's talking about the Earth's radius. So clearly they're talking, if this is true, about a sphere which has a radius, and that this is the basis for some units of area. The third geodetic aspect is apparent in a standard of mass, hypothetically based on the density of water. And a fourth link with nature emerges from certain weights that look as if they were made to express the density of gold. So the density of water and the density of gold. So you have the Earth providing some of the standards, and then you have the density of water and the density of gold. Now, the density of water is a bit problematic because, it can change with temperatures. It is only in the light of the metric system that the first and second of these coincidences are visible. They could not have been discovered in antiquity, and there is no record of any traditional knowledge of such an origin. Certainly, the Greeks were unaware that the circumference of the Earth measures 216,000 Greek stades. Okay, this is interesting. So the Greek stade, well, there are several Greek stades, but the one he's talking about fits in to the polar circumference of the Earth 216,000 times, a sexagesimal number. Interesting. The Greek stade, I'm continuing reading now, measures 600 feet, and the best evidence for the length of the Greek foot is the platform of the Parthenon. So this is the temple in Athens, famous temple, which is 100 Greek feet in width by 225 Greek feet in length. It was measured in 1750 by Stewart and a century later by Penrose. The mean of their measurements gives a Greek foot that corresponds in length to 1/100th of the sexagesimal second of arc on any great circle of the Earth regarded as a sphere. So in fact, he's not saying necessarily the polar or the equatorial, but he is saying that the Greek foot, which is, by the way, 12.15 inches, 12.15 inches, goes in to the Earth's circumference in that way. And it's really, I think, fair to say the polar circumference that most of these measurements are connected to. And if I put that into a calculator, so 1215 inches, which was so the length of this foot, then we can scale it up a bit times 100 times 60 times 60 times 360, because we have seconds and minutes of arc and then the degree system. And what do we get converting that into miles? We get something that's actually quite close to the current estimate for the polar circumference of the Earth. We get 24,852.27 miles. So this is already really interesting. So the Greek foot is linked to the division of the Earth into degrees, minutes, and seconds of arc. And it's pretty accurate. But what he's also saying is the Greeks didn't know about this. So the Greeks were actually quite good at they were interested in trying to guess the size of the Earth. And there are various reports about the size of the Earth. For example, Aristotle says 400,000 stades. But we don't know what stade he meant, because there are different kinds of Greek stade. It's a bit complicated. Then there's Eratosthenes. So he made some measurements, and different reports say different things. So his work is lost now. But Cleomedes says that Eratosthenes said the Earth was 250,000 stades, and others, so Strabo, say 252,000 stades that he said. Anyway, the point is that there were various values going around the classical world in terms of what the Earth's size was. So they obviously regarded it as a sphere, and they were interested in the size, and there was interest in metrology. And this was obviously a really important subject in ancient Greece. In fact, one of the last things that Plato said before he died was talking about the Earth as like a football in Theaetetus. Okay, to go back to the text, to Berriman's text. The estimate of the Greek foot does not rest on these measurements alone. It is confirmed by measurements of the Roman foot made a century earlier by Greaves. The relevance of this reference to the Roman foot lies in the fact attested by ancient writers that the Romans used the Greek stade of 600 Greek feet, but rated it 625 Roman feet. Any lengths purporting to be those of the Greek and Roman foot must conform, therefore, to this 25/24 length ratio, and it is the need to apply this test to the measurements recorded by Stewart and Penrose that makes it necessary here to refer to those reported by Greaves. Okay, so what's going on here? So he's saying that this Greek foot went in 600 times to make a Greek stade. So 600 of these feet make a stade. So again, the sexagesimal system. But the Romans compared that particular stade to a stade of theirs and said, well, that's actually 625 of our feet. So therefore, we know now that the Roman foot, in terms of its ratio to the Greek foot, was 25/24. So slightly smaller, 11.6. So I can show you this. So it was slightly smaller. So if we do that, 12.15 times 24 divided by 25, this is what we get. This is the ratio. So this gives us a value for the Roman foot using this information, 11.664 inches. Now, again, there are variations on the Roman foot. It's not straightforward, but this works. So then Greaves, we're coming up to Greaves now. So the Parthenon was measured twice. The same result was got by these two people, Stewart and Penrose. But then we're going to Greaves. So Greaves is an interesting character, and he's actually very important in metrology. He was really interested in this subject. He went to Rome and he went to Egypt. Anyway, let's read. Greaves. He was Gresham Professor of Geometry and about to become Civilian Professor of Astronomy when in 1639 he equipped himself with suitable instruments and went to Rome specifically in order to ascertain the length of the ancient Roman foot. In the Vatican Gardens, he was fortunate to find a monument exactly suited to his purpose. It had been made in the 1st century AD to commemorate a young architect named Statilius Aper, who had died in his 23rd year. This large and elaborate cinerarium is now in the municipal collection, and the instruments of the deceased's profession that it portrays in relief include the Roman foot measure that Greaves reported to contain 1,944 such parts as the English foot contains 2,000. This makes the Roman foot exactly 24/25 of the Greek foot derived from the Parthenon. So basically he's saying that what Greaves found independently and long before is exactly what the others found at the Parthenon. Well, in relation to this ratio between the Greek and Roman foot. So that matches. So that seems to be true. And then when you have two sources confirming the same thing, there's a good chance that this is actually correct. And especially it just consolidates the data. So we have now the Greek and the Roman feet. So continuing on, the Roman foot was rated 16 digits, which makes the length of this digit 1/54 of a meter. Okay, so more things to talk about here. Digits. These are the divisions. This gives us the word finger, by the way. Oh, in French. Digits. So basically, it's about the number 10 because we have 10 fingers. And this is the names of the name of the divisions that we have in many ancient units. So, for example, our foot today, where the foot is used, is divided into 12 inches, but the Roman foot is divided into 16 digits. So, and then he talks about the meter. This is interesting. So he's been criticizing the abandonment of this ancient system, but he's not criticized the meter. In fact, he's talking about it now, and he's actually bringing it back into the fold because he's saying that digit is 1/54 of a meter. So 54 of these Roman digits in a meter. 54 is a good number, by the way. So it's a multiple of 9, which is important. There are 100,000 of them in the terrestrial minute of arc, measuring 6,000 Greek feet, and it is convenient to call this distance a geodetic mile. So geodetic meaning related to this division of the Earth into degrees and seconds and all that. If the Greek foot had been 1/100th of an inch longer, the proportional length of 6,000 such feet would have been equal to the Admiralty sea mile of 6,080 feet. Oh, so he's saying very close. So 1/100th of an inch, that's not very much. So he's saying there's a potential connection there. The Roman digit was equal to the Egyptian digit, of which 20 made the remen. So the remen is another important unit of measure. It's 14.58 or 14.5833 inches. And Griffith, when Professor of Assyriology at Oxford in 1891, identified the diagonal of the square on the remen with the cubit that Herodotus called royal. So what he's saying is that there's some geometry at play here. So we talked about the Egyptian royal cubit. If you take a remen and make a square out of, like, the square is 1 remen per side, and then you take the diagonal, so multiplying it by the square root of 2, then you get an Egyptian royal cubit. So he says this was found by Griffith. And that's actually pretty well accepted today in historical metrology, this geometric relationship, so the remen and the Egyptian royal cubit. This relationship implies that the square on the royal cubit is twice the area of the square on the remen and was of practical convenience in land measurement. In particular, it made the land unit that the Romans called jugerum equal to the square on 96 royal cubits. And this area was 5/8 of the English acre. So don't worry too much about the numbers here. The main thing he's saying is that they're all connected. That is to say, units of length, units of area. There's geometry involved. So, for example, multiplying by the square root of 2. He's talking about land units and this unit of 96 royal cubits, which is in a particular interesting ratio to the English acre. And again, once we have an English unit of measure here mentioned. So we've talked about the inch already, and now we have the acre. And he's saying it's 5/8 of the English acre. So I'll just show you this bit here. Oh, it's just here. So the important thing is he's connecting these measures. He's connecting these ancient Roman and Greek and Egyptian measures to each other and to the English units of measure. That is to say, it measures 100 English square poles exactly when the royal cubit is defined as 20 inches and 5/8 of an inch. 100 English square poles. So the pole is a unit of measure that we haven't had for a very long time, and you can take the square on that. So the square basically composed of one pole per side. That gives you an area of land. And he's saying that that's 100 such square poles, exactly that when the royal cubit is 20 inches plus 5/8 of an inch. So we've kind of lost this habit of expressing units of measure in this way. So I'll just show you what that means. 20 plus 5 divided by 8 is this. So that's just converting it to decimal, 20.625. Now that's not actually what he had said in the beginning. He'd said 20.62526, but he's just saying this is another alternative. So in terms of the 12-inch foot, the pole measures 16.5 feet. That's exactly what it is. So the pole is this ancient English unit of measure, ancient, and it's 16.5 feet. But formerly, it measured 15 feet in terms of a foot of 13.2 inches. So this is the Saxon or Sumerian foot, 13.2 inches. Sometimes it's associated with the Drusian foot. There are a few little niggly things about which is the correct terminology. John Neal used to get very annoyed about this. But anyway, 13.2 inches is the value. Let's worry about the value. So 13.2 inches used to be a really important foot in Britain. And it disappeared over time. It might seem strange now if we have a foot of 12 inches that we would then have a larger unit of 16.5 of those. Why 16.5? But it's because originally that pole was linked to the Saxon foot. So the Saxon foot of 13.2 inches would have gone 15 times into that particular pole. Hence, now it's 16.5 feet in a pole, which sounds a bit odd, but it used to be 15 Saxon feet. Or it can be regarded as a length of 10 cubits of 19.8 inches. Okay. And I have identified this as a Sumerian cubit of 30 shuzi in terms of the linear scale on one of Gudea's statues of the Louvre. Gudea was governor of Lagash in southern Babylonia about 2175 BC, and the statue shows him seated with a tablet on his lap. On the tablet is the ground plan of a temple and the linear scale. And of this, I have a copy that has been checked by the authorities. So what is he saying there in this paragraph? This is all in one paragraph about the English foot and the Saxon foot and the Sumerian cubit and the governor of Lagash, which is Gudea. These are all really connected. So he's saying that there's this unit of ancient Sumeria, which is 30 shuzi in length. The shuzi is a unit of length, so 0.66 inches. Sometimes it's considered 0.6525. But 30 shuzi make up a pole, which is also 16.5 English feet, which is also 15 Saxon feet. Sumeria, Britain, Saxony, there we are. So this is taking basically the system that these measurements belong to back to at least 2175 BC. I think there's a little illustration on the next page of the statue, which has lost its head, but the important part is still there. Apologies, Gudea. So, to continue, the Sumerian cubit was equal to 24/25 of the royal cubit. Where have we come across this? 24/25. This is the ratio between the Greek and the Roman foot, which means that 12 myriad royal square cubits were virtually equal to 13 jugera. This is the Roman land measure. This relationship has historical significance because Herodotus remarks that Egyptian warriors were rewarded with 12 setats of land, setat being the Egyptian name for a land unit of 1 myriad royal square cubits. And Bishop Epiphanius, in the treatise on weights and measures that he wrote in AD 392, says that the Palestinian yugon of first-class land containing 8 myriad Palestinian square cubits was equal to 13 yugara. It is apparent, therefore, that the area ratio of the Palestinian to the royal square cubit was as 3:2. Also, it can be shown that the Palestinian field of 1 myriad Palestinian square cubits was equal to 65/64ths of the English acre. So again, we have the English acre, we have the yugara, the land measure of the Romans, a Palestinian land area measure, and the Egyptian one, and they're all connected. So even though this seems a little bit number heavy, isn't it interesting to think that it's just one system? Well, we have looked at every single measure in existence at the time, but it seems to be that the important units of measure that are being used at least are all connected. To continue, the English acre is the most intriguing of ancient measures. Okay, so already saying it's an ancient measure and it's intriguing, which we can probably agree with now, because it is virtually equal to the hypothetical geodetic acre defined as 1 myriad millionth of the square on the terrestrial radius. So we were talking about the radius of the Earth being a particular standard that could be used then for areas of land. And so that's where the standard would come from, the size of the Earth, but in terms of its radius. But what he's saying is that this is part of then a decimal system. So talking about myriad millionths, so it's like basically dividing by 10, 10, 10, 10, 10, 10, 10. You know, this is like a decimal division. So it's not just sexagesimal, it's decimal as well. And it's basically, you can bring that back to the radius of the Earth. If both acres are expressed as squares, the difference between the lengths of their sides is less than 1 part in 1,200. The geodetic acre can also be defined as measuring 1 myriad square cubits in terms of a hypothetical cubit, equal to 1/10 millionth of the terrestrial radius, and it's convenient to call this cubit A. Its former existence is as plausible or as incredible as a cubit derived from the sexagesimal division of the Earth's circumference. So cubit A is basically a unit that Berriman puts forward as almost like a placeholder, like a hypothetical cubit that would tie these other elements of the system together. So just to continue a little bit further, if there is any validity in the hypothesis of a geodetic acre, it would seem necessary to suppose that it was the prototype of the Palestinian field as well as of the English acre, and this would imply that the Palestinian cubit originated as cubit A. It is described by Epiphanius in the same way as Ezekiel describes the cubit of the altar, that is, a cubit and a handbreadth. That's just the width of the hand, it's a unit of length. The cubit of reference in this description is the royal cubit. If the English acre is drawn as a circle, it can be inscribed in a square, representing the obsolete Scottish acre. Okay, so this is now coming back to more northerly climes. We've got English, Scottish, and then he's going to mention Irish. So there's some geometry at work here. So the obsolete Scottish acre, and if this is expressed as a circle, it can be drawn in a square Irish acre. So they're all connected, squares and circles. Add only 14 square yards to the Irish acre, and it is the area of a circle 100 yards in diameter, which is the published size of the outer earthwork circle at Stonehenge. Again, so we're back to the ancient world. A square enclosing this circle would have an area of 1 myriad square yards, and this probably was the size of a Hindu land unit called Nivatana. In any case, it is relevant to remark that the area of the swimming bath found at Mohenjo-daro in Pakistan, 100 square yards. That is English yards. It's obviously very intriguing. Mohenjo-daro, meaning Mound of the Dead, is the site in the Indus Valley where excavations revealed for the first time the former existence in that region of a culture contemporary and comparable with those in early Mesopotamia and Egypt. Among the smaller finds is a piece of shell on which a linear scale is most carefully marked by fine saw cuts. Separated by 5 divisions on the scale, there are 2 lines specially marked, and the distance between them is exactly 2 Sumerian shuzi. I call this length the Indus inch. So we talked about the shuzi just now in relation to the Sumerian cubit and the Sumerian foot, 0.66 inches or 0.6525, depending on, yeah. If we're going to go with 13.2 inches for the Saxon foot, then we have to go with 0.66 inches for the shuzi. And this unit then, which we've talked about in relation to Sumeria, is in Pakistan. So he's saying that this is it's very precise, deduced from the markings on this shell that was found. And he's calling this the Indus inch. 2 Sumerian shuzi, 1 Indus inch. Continuing on, a multiple unit representing 25 of these Indus inches survived in the traditional yard that Akbar standardized when he came to the throne in 1556, and still survives in the 33-inch re-standardization of this yard by the government of India in 1825. British interest in Akbar's yard arose from a desire to establish the size of a land unit called the biga. It was found to be equal to the square on a linear unit called jarib, containing 60 of Akbar's yards. But it was not realized that this made the biga exactly equal to 100 English square poles. Back to the square poles. So the square pole, the pole is 15 Saxon feet, 16.5 English feet, and it's related to ancient Sumeria, but now we find it again in Pakistan and in India, Instead of perpetuating this interesting tradition, the authorities imported the English acre into Indian metrology and divided it into 100 parts called decimals. Strange. Anyway, interesting that it was the same system, right? The double yugarum, so the land measure is the yugarum, so the double yugarum of the Romans, called heredium, survived as the arpent in the pre-metric metrology of France. Arpent, A-R-P-E-N-T. But its importance in historical metrology is quite overshadowed by the significance of the French livre. In 1742, the Royal Society of London and the Royal Academy of Sciences at Paris collaborated in the direct comparison of English and French metrological standards, and the results showed the livre to be 108 divided by 100ths of the present English standard pound. So the livre literally means pound, and it was connected by this precise ratio to the English pound, 108 over 100. Now, there is in the British Museum a Babylonian stone weight that I call Mina N, because it is engraved with a cuneiform inscription certifying it to be a copy of one that Nebuchadnezzar II made to accord with an earlier weight owned by a former king named Shulgi, which belonged to the 3rd dynasty of Ur and reigned about 2100 BC. This inscription, therefore, is documentary proof of intention to preserve a standard of mass for at least 1,500 years, but it has not previously been noticed that this standard was the livre, the French pound. The mass of Mina N is 2 livres, and this makes it equal to 3 Roman libbre. So here we have the French system, the Roman system, and we're going back to Nebuchadnezzar in the kingdom of Ur. So this is all kind of amazing. This one system that has continued and continued over such a long period of time. So the French livre, which he says is connected to the British one in a particular ratio, this French livre goes back to at least 2100 BC. To continue, moreover, I find that a hypothetical talent of 60 livres would be equal in mass to a Greek cubic foot of water at maximum density. There is now no physical example of this talent, but it can be identified with the water weight of the biblical measure of capacity called bath. A bath is actually a unit of measure, a volume. if the cubit used in the measurements of the molten sea is interpreted as cubit A. This is again his hypothetical cubit, cubit A. The tradition of this talent as a unit of measurement seems to have been preserved in modern times by the tun of wine weighted 252 troy gallons, which is equivalent to 36 Roman amphorae or 32 Greek cubic feet. Again, all these connections. So I don't want to get too much into the numbers, and but the fact that these units are all part of a system, and twice now he's taken us back, 3 times he's taken us back to prehistory. So he's mentioned Stonehenge, he's mentioned Kingdom of Ur, he's mentioned Gudea. So these units of measure that existed up until quite recently, so for example the pole, the French livre, but also still exist, like the English pound, the English and the yard, they're all connected to this very ancient system, which is basically going back into prehistory. In English historical metrology, the present standard pound is associated with the 14-pound stone in a system of mass known from medieval times as avoir de poids, sometimes avoir du poids. And it is in terms of this system that Edward III defined the mass of the sack of wool as 26 stone, that is 364 pounds. This rating reflects the importance of England's export trade in wool, for it was adapted to the 500 libre, so 360 pounds, standard used by Florentine buyers. So this is when wool was basically huge in Britain. It was exporting wool and it was making people a lot of money. This sack of 500 libre was an exact English standard in another system where it was rated 350 mercantile pounds or 5 futmals. Futmal being the name of a mass equal to 100 libre with a rating of 70 mercantile pounds or 72 pounds avoir de poids. A document of this period, devoted entirely to weights and measures, defines this sack of wool as equal in mass to 1/6 of a cartload of lead. This cartload therefore weighed 2,000 livres or 30 futmals, and the tradition of this relationship and of the name futmal both survived in the customary fodder of lead that now weighs 6 sacks, equals 156 stone in the avoirdupois scale. Sometimes the mercantile pound, the libra megatoria, was confused with the pound avoirdupois, and it was known as the pound of 25 shillings at a time when the pound of 12 ounces troy was called 20 shillings weight, but its early significance was 2 tower marks or 16 ounces in this scale. Now, it gets a little bit complicated, and that's the thing with historical metrology. It is really complex. There are all these different names of units. So, for example, in terms of geography, so we have Roman and Greek and Egyptian, even though they're all from the same system, it's already confusing. But then it just gets so confusing. So we have, like, even in, say, the English history of weights and measures, you have the avoirdupois, and you have troy, and you have different kinds of pounds, and then you have different kinds of gallons of wine, and all this kind of. So basically what he's saying here at to the end of the page is that all of these go back to very ancient times. The tower pound of 12 tower ounces was so called because it was the standard of mass in use at the Tower of London Mint until Henry VIII, possibly on the advice of Cardinal Wolsey, abolished it in favour of its rival, the troy pound. And actually this is interesting as well, wondering why did people have this kind of pound and that kind of pound, and why would they abolish one and support the use of another? Probably Ethelred the Unready was referring to a prototype tower pound in his law requiring those in charge of towns to stamp their weights according to the standard of his mint. His rating for it was 15 oars. The masses of the Roman libra tower pound, troy pound, mercantile pound, and the French livre were proportional respectively to 14, 15, 16, 20, and 21 such oars. The mass ratio of the pound avoirdupois to the mercantile pound was 35, as 35 is to 36. There we are. Okay, so we're going to stop there in terms of the reading. We only made it to page 7. There we go. There's a lot to take in. It's very difficult to just kind of read this book in one sitting. I don't think you could really. There's so much to take in. But what's really interesting is, on one hand, the historical research, and on the other hand, the connections that he's made. So he's researched the literature. He's gone and measured things himself. He's gone and asked the museum authorities for their confirmation. And he's made connections through geometry, through reasoning. So it's just fantastic book. So there we are. So this is Berriman's Historical Metrology, and it's basically, it's quite long. It's like 200 pages more, and it's got just some really interesting chapters, including one here which people today might find very interesting: the weights and measures of the United States of America, which go way back as well. They're in no way new. They're really ancient. Okay, so thanks for watching.